class 15, I'm going to do a series of examples, and the first one is very much the same as the maximum shear stress theory class 14 example. It's the same one actually, but I'm just going to now do distortion energy theory there, so I might want to look at the other example or the examples from class 14 where this is the case. So this is problem 5.1c and 5.5 from Shigley. So let's see. I want to steal the numbers. There you go. And we have a stress state of 100 megapascals here in tension. So that's going to be 100. And then we have a negative, which ends up being that direction for shear of 75 megapascals. And from a previous one, we found, I should say the first principal stress, right? Because this is uniaxial, so you can expect that one of the principal stresses is going to be in tension, and one of them is going to be 0, and then the third one is going to be in compression, right? So I'll call it as negative, but I mean compression is negative. And based on this, the maximum shear stress theory, we found that we got 1.94 was our safety factor. So that's from the previous one. But now let's find the von Mises stress. And we can use either of two equations because we already have this, the principal stresses. So we can use this equation right here where we have sigma A squared minus sigma A times sigma B plus sigma B squared. Take the square root of the whole thing, where this is sigma A and this is sigma B. So plugging these numbers in here, specifically because I want to address the minus sign there, 140 squared minus 140 times minus 40, right? So you see that minus sign is going to play a role right in here. Whether it's in compression or in tension, we got a different answer, right? We got minus 40 here, but this is squared, so that one doesn't really matter. So the sign does matter right here, where it won't in some cases. 163.9 megapascals. Now, if we hadn't gone through the trouble of finding the principal stresses, we could have just gone to this right here in the beginning. And because it's uniaxial, we can use the simpler equation of sigma x squared plus 3 times tau xy squared. Take the square root of that, right? So you can try this out yourself, right? So just take 100 squared plus 3 times 75 squared square root, and you get we'll get the same number. And I didn't leave a lot of room for myself, but get the safety factor here. We were told that we have 350 is the yield strength. So we have 350 divided by 163.7, and I get that it's 2.14, right? So the answer is 2.14, keeping it down to only 2 decimal places for my safety factors as my preference. You can see this one is larger than that one, and I just start to think about this, think what that means. Having a smaller safety factor means we have less margin, all right? So that means that we're closer to failure, according to him, than we are to him, right? So what we often say is that this will be more conservative than this. Let's take a look what it looks like on the failure loci. All right, so 350 should be like right in there. Right? So this is the maximum shear stress theory boundaries. I didn't bother putting it in there, but I could have. Right there. But it's good to have them on here so that you can have a comparison. Or comparable, right? I don't need to draw the other side of it. It's symmetric right up there, right? Well, I might as well finish it. Might as well finish it. Why not? Don't be lazy. All right, so our principal stresses, that's what we actually plot on our failure loci. Well, they were 140 and negative 40. So this is 110. No, this is 120, 140, right there. 160, 180, yep, right there. And then 40 went at negative right there. So we end up in being at that spot right in here. We'll try to do our best to be as accurate, as precise, accurate, I don't know, one of those, as possible. And you can see this is where it crosses here for the maximum shear stress theory, and this is where it crosses for the distortion energy theory. So we might call this O, A, B, and C. I'll take my millimeters here, and according to this, let's see, I will carefully look, and it looks to me that I have 21, 2, 3. It looks like 23. So I'm going to say that OA is approximately 23 millimeters. And then looking at this, we already did this once for maximum shear stress theory. Here's for distortion energy theory. Let's see if I can. That looks like it's almost 49. That looks really close to 49 to me. Let me say 48.5. Going to incremental millimeters is like that's a little intense. So we say that the distortion energy theory, by way of graphical analysis, is OC, this length divided by this length right there, OA. So we get 23 divided by 48. Nope, 48.5. Sorry, 48.5 divided by 23. I kind of fixed it. Kind of, now it looks pretty awful. Fix it. I'll make it look 23. All right. And what are we going to get? 48.5 divided by 23. We get 2.11. Let's call it. So there you go. There's a comparison between there. We're slightly off, but it's all about the pencil thickness, right? It's about the lead thickness onto the thing. So I'm going to do, maybe I'll do the other example while we're here, right? Because they're so quick. So I'll do, yeah, let's do the other example. No reason to do a whole separate video for the second example. So here's the other example right here. Just to show you in a different quadrant, maybe. This one noticeably was in this fourth quadrant, which would be like case 2, right? And that happens right here, where, you know, because we had a Mohr circle that like was crossing across this thing, so we had a sigma A here and a sigma B here. So that's the case where one of them is going to be negative, so it ends up being down here in that quadrant. But let's try this one right here. We already have the principal stresses. It's kind of a easy one to do. And in our this setup, this this strength, so we looked that up and we found that it was 37.5 KSI. And then I think for maximum shear stress theory, what we found is we got 1.5 from previous previous video doing this example. So now we want to get the von Mises stress off of this. And so we can, these are the principal stresses, so we could just go ahead and use this a squared minus a times b plus b squared of all the stresses, right? So plug them in there and get 25 squared minus 25 times 15 plus my 15 squared. Take the square root, and I get that it's 21.79 KSI. So if I want the safety factor from the distortion energy theory, I take the yield strength and divide it by von Mises stress, and I get 37.5 divided by 21.79, and I end up with 1.72 KSI. And I want to take a look and see what that looks like on the principal stress loci. Let me go ahead and draw in my maximum shear stress theory envelope. Let's be close to that, right? Somewhere in there. And I don't actually need to do the rest of them, do I? No, I don't. I need some coffee. Somebody go get me some coffee. Oh, wait, I'll go do it myself. All right, so anyway, I didn't bother with this guy. Okay, so plotting these out, we have 25 and 15. So it would be 25 is going to be like right there, and 15 is going to be right here. So plotting these out, that looks like it's going to be right there. And we will plot out from the center. And I will call this O, A, B, and I'll call this guy C. And so we're going to start out with here in millimeters. That looks pretty close. I could shift it one way or the other. I could shift it. That looks like it's pretty close to being 40. 1, 2, 3, 4. 44. And then OC. That looks to me like it's going to be 76, right? There's 1, 2, 3, 4, 5, 6. Go 76. OC is approximately 76 millimeters. So my distortion energy approximation through graphical method is going to be my OC divided by OA, which is going to be 76 divided by 44. 76 divided by 44 is 76, enter 44, divide 1.73. So you can kind of see where it landed, right? So here's the 1.5 right here. So you can see it's really because it's near this big gap. If we were to, say, get a stress state that was like along this line right here, like a 45 degrees, which means that A and B would equal each other, right? And that's the only way you can get a 45 degrees right here, when sigma A and sigma B are equal to each other. And you would see that they'd get the same safety factor. Interesting, huh? As the maximum shear stress theory. Another thing that's interesting is like when you you'd also get a maximum will occur when sigma A and sigma B are equal to each other, except sigma B is negative, right? And this happens in the case of a pure shear, right? So we could see that if we had pure shear on a Mohr circle, that plotting of that would be just like right there, right? So we would have a Mohr circle that looked like this, so that sigma A and sigma B were equal to each other, but opposite in sign, and so that would be along this line right here in pure shear. So that's an interesting thing to know. It's also it could possibly occur. Let's see. No, I guess up here, if this was just a pure pressure vessel, right? So in the pure pressure vessel, longitudinal is exactly 1/2 of the hoop, right? So this right here would be a pressure vessel with no other loadings on it. But I often will put a load on it, which I will in the next example. So we will make another video, but this is the end of the just pure examples. It's 14 minutes long. It was worth doing both things in one video.